Hello, CS111 students. This is my problem set video for problem set 3, task 2 on the accelerating jig. Just as a note, these problem set videos are optional. You can read the problem set description, which is what I'll be doing right in this video, instead of watching the video if you prefer. For this problem set, you have a choice. You can do task 2, which is what I'm covering here, or you can do task 1 instead. You only have to do one of those two tasks. You must do tasks 3 and 4. So you'll be doing a total of 3 tasks, either 1 or 2, and 3 plus 4. This task 2, is about making music with the synth.py module. And depending on which task you chose to do last week, you may have already used that module, or you may be coming to it for the first time. The other optional task that you can do instead is task 1, and that is on using Turtle Graphics to draw stuff. So you have a choice between drawing and music. This task is going to help you review material on custom functions and how to use functions, parameters, how to use functions together to achieve a complicated result. But you don't need to use booleans or conditionals at all in this task. So it's a little bit of a review task for the stuff that we covered last week. So I mentioned that you'll be working with a module called synth.py for this task. This allows you to create wave files using Python functions to specify which notes to sort of compose into a piece. And the library does some very simple sound synthesis. It's not particularly fast, and it's not particularly beautiful in terms of the sounds it produces. But it does allow us to do some neat stuff with programming audio. There are detailed instructions in problem set 2, task 4, covering the basics of how to use the library. And if you did not do that task last week, then you should go back and look at those instructions a little bit. We also have reference pages for the synth module that cover some of the stuff there as well. So it is up to you to sort of use those resources to familiarize yourself with how to use this module. There are links in the problem set to those resources that you can explore. And so what are we doing in this task? Well, at a high level, there's a classic Irish jig called the Irish Washerwoman. And we're going to be writing code to create part of that tune. Just the melody, and not even the whole melody, just the first part. But that tune involves several repeated phrases, so we'll have an opportunity to put functions to good use. There's an audio clip in the problem set description that you can listen to for yourself, and you can also download the WAV file behind it. To make things more interesting, and you can hear this if you listen to the clip, each note in the song is slightly shorter than the previous note, so that the pace of the song is sort of gradually increasing as the song goes on. And to achieve this, what we're doing is we're taking the duration of each note and setting it to 99% of the duration of the previous note. There are 48 notes in the song, so the duration will shorten by a factor of 0.99 to the 47th power, which is 0.6236. So the duration of the last note is about 62% of the duration of the first note. But that speed up is sort of very, very, very gradual. It's hard to notice at any particular point in time, but by the end you're like, oh, this is faster than at the beginning. So how are we going to do all this? Well, you'll have to write a total of 7 functions, which are outlined in the subtasks below. You must write a non-empty doc string, a documentation string, for each function that you write, which is just a general requirement that we usually have on all our problem sets. So again, in terms of how to use synth.py, please do check out that section from the previous problem set if you didn't work on that one last time. If you did, you're probably already familiar with the basics. The functions that you will need are add note, step up, step down, and set pitch. That's literally it. Don't need to worry about changing the volume or the instruments or beats or rests. Just those 4 functions. And again, we have links to the reference pages for those 4 functions there. You can read a little bit more about them. Set pitch was not explained in the previous task, but it's pretty basic. It basically just says, hey, whatever the current pitch was now, I don't care. I'm going to throw it away. Here's the new pitch. I want to be the current pitch. And then the next note you play will use that pitch unless you call another function like set pitch again or step up or step down before that note is added. So what are our subtasks? Subtask A is really the engine of the whole thing. It's a function called 3 notes. And the jig that we're written is written in a timing where there are often groups of 3 notes that go together. You can kind of hear it if you listen to it. And so since we have these sequences of 3 notes that go together with each other, we're going to write this function 3 notes so that it's very flexible and can produce any of those sequences. So instead of adding 3 specific notes, like, oh, this one, then 2 steps up, then 1 step down, 3 notes is going to have 3 parameters. The first parameter is the number of steps up, or down if you give a negative number, between the first and second notes. The second parameter is the number of steps up or down if negative, between the second and third notes. And the last parameter is just the duration to use for the first note. So we're going to add 3 notes. We have these 3 parameters that control how far up and down we go in pitch between the first and second and third notes. We can use those parameters to be very flexible and create a lot of 3-note patterns just by manipulating the parameters. 3 notes has to call add note 3 times to add the notes back to back. If you just call add note, add note, add note, they'll already be arranged that way. And it has to sort of use the given pitch intervals between them, right, using step up or step down. Note that step up can accept a negative parameter, so you don't necessarily need to decide whether you're using step up or step down. We want, remember, throughout the whole song, for each note to be 99% of the duration of the previous note, right? Multiply that previous duration by 0.99. And so that should be true in 3 notes as well. We're given a duration to use for the first note. We'll multiply that by 0.99 to get the duration of the second note, and then multiply that by 0.99 again to get the duration of the third note. And obviously, if we call 3 notes, then the duration that we gave it is going to be a little bit shorter by the end of the 3 notes. So 3 notes has to return the duration of the last note that it added to the song. So it's going to add 1 note, a very slightly shorter note, a very, very slightly even shorter third note, and it should return the duration of that third note. Finally, just like in the previous problem sets, synth.py task, 3 notes has to maintain an invariant. And that invariant is that by the end of the function, the current pitch value should return to the initial pitch that it started at. Even though the last note may not be at that pitch, we want to return to that initial pitch so that whoever calls us won't have to worry about, okay, well, I called 3 notes and now the pitch is this, so then I need to set it to that, right? They can just say, I called 3 notes and it did its thing and it didn't change the current pitch. So we provided a testing function called test 3 notes. It calls your function twice and prints some messages if you have incorrect duration results. And it also prints a text description of the notes that it adds, in addition to actually playing them. And you should see the following printed output when you call test 3 notes. We've given an example of that in the problem set description. We've also given you an audio file there that you can play to listen to how it should sound. If you're like me and I don't have really, really great pitch, listening to how it should sound is not a great measure of whether I'm correct or not. So I prefer to like inspect the text and compare, hey, what did mine print versus what did that one print? And also potentially like throw that text into like a difference checker. We have the difference checker website link, maybe not in this task, but it was in several of the previous tasks. And just sort of carefully check for any differences in the text about the specific durations of those notes or their pitches or their volumes, although volume shouldn't change at all in this task. So that is subtask A, 3 notes. And that's, like I said, like the foundation or the engine of the whole jig that we'll do, because it provides us this flexible way of saying, hey, those 3 notes, now this pattern, now this pattern. In subtask B, what we'll be doing is identifying some of the 3-note patterns that happen in this song and simply making custom functions to pick out those patterns. So we have 2 introductory notes in the song, then we have a kind of high-low-low pattern, and then a low-high-high pattern, and then there's like an up-down-up pattern, and then a 3 falling notes pattern. And then that entire set of 4 3-note patterns repeats itself 3 times, although it kind of shifts in pitch for the middle copy. And that is most of the melody. There's a few other notes at the end, but like that is most of the melody. So how can we do that efficiently, right, elegantly using functions? Well, we have our 3-note function. What we're going to do is write 4 functions that capture these 4 different repeating patterns, plus a combining function that does all 4 of those 3-note patterns, so 12 notes together. And we'll be able to then reuse those functions very elegantly to produce the whole pattern. So we're going to define up, down, 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 up, up, middle, low, and 3 falling. Those are the names of our 4 pattern functions, and each one of those functions is going to produce a particular pattern of notes. So up, down, down starts on a high note and then has 2 low notes. It has 1 parameter, which is just the duration of the first note it adds. For up, down, down, the second note is 2 steps below the initial note, and the third note is the same as that second note. And your up, down, down function and all these pattern functions really should just be one line of code that says, okay, I'm going to call 3 notes with these specific parameters for the steps in between. And just like 3 notes, up, down, down has to return the duration of the last note it adds, and of course it can get that duration from 3 notes that it calls. So up, down, down, and these other pattern functions are really just like very, very, very straightforward functions that just have like one line of code in them. Down, up, up is complementary to up, down, down. It has 1 parameter and the same result value, but the pitches are different. For down, up, up, the second note is 3 steps above the first note, and the third note is the same as the second note. So up, down, down was like, this pitch, 2 steps down, 2 steps down. Down, up, up is starting pitch, 3 steps up, 3 steps up. That is like both those pitches are the same at 3 steps above the starting pitch. Middle, low is the third pattern. Again, same parameter, same return value, and the note sequence is starting pitch, then 2 steps below that, and then returning to the same starting pitch again. And then 3 falling is our final pattern. It has a starting pitch, a note 1 step down, and a note 1 more step down from that. So it's note, step down, step down. And so those 4 pattern functions, each of them, really, really, really simple, should be super quick to write, are going to be the main functions that we use for a function called phrase. And phrase is going to capture this repeating phrase that happens. It's 4 different measures of 3 notes each, repeats the whole phrase 3 times. And phrase, like those other pattern functions, has 1 parameter, the duration for the first note that it adds. And just like those individual pattern functions, it's going to add shorter and shorter notes each time. It has to return the duration of the last note it produces. Unlike those functions, you're not allowed to call 3 notes within phrase. Instead, you have to call those functions you just defined in phrase, right? And they're there to make the definition of phrase still fairly straightforward. The one tricky thing is you're going to have to thread the duration value through these different functions, right? Give it as a parameter to this function, then take the return value, and then shorten that return value, and then give it as a parameter to the next function, and repeat that pattern throughout. Phrase starts with whatever the current pitch is, right? We don't know what that is, but whatever that is, we'll start there. That's the first note of an up, down, down pattern. Then it has a down, up, up pattern beginning 5 steps below the initial pitch. Then it has a middle, low pattern that starts at the same pitch as that first note. And finally, there's a 3 falling pattern that starts 2 steps above the initial pitch. So all these things are based on the initial pitch. It's up, down, down at the initial pitch, down, up, up 5 steps below, middle, low at the same pitch again, and then 3 falling starting 2 steps above the initial pitch. And you'll notice that with 3 falling, since we stepped down twice, that'll bring us right back to that initial pitch at the very end. So we've provided testing code for your phrase function called test phrase. And like test 3 notes, it checks the return value of a function and it prints out the notes that are added. If your phrase function is correct, then we've provided what the output should look like exactly in terms of printed output. And we've provided an audio file that you can use to listen to what that should sound like. Just a note here that since there's only 12 notes in the phrase and our speedup is sort of very subtle, it's going to be hard to notice the speed up just over the course of a single phrase. So you might listen to it and go like, is it really speeding up? Am I doing something wrong? Check the printed duration of the notes, right? If our first note is 0.2 seconds, which is how the testing code works, then our last note should be 0.179 seconds, right? It's a tiny, noticeable but not obvious speed up that's happening. So subtask C is to play the whole song. We have our phrase function, we have 3 notes, we have our individual sort of pattern functions. Now we're ready to create a function called jig that adds notes for the entire song, or at least the first part that we're requiring. The jig function takes one parameter, which is, surprise, surprise, the duration of the first note. And it has to produce the following patterns. So to start things off, there's a 2-note lead-in. Each of these notes actually uses half of the standard duration value. So even though we said that the parameter to jig is like the duration for the first note, actually it's the duration for the first 2, well, it's double the duration for the first note. It's most of the duration for the first 2 notes. So the first note is half that duration value. The second note is half of 99% of that duration value, because we still shorten every time we see a note, even if it's not a full note. Those 2 notes uses the specific pitches D5 and C5. And those are just variables from synth.py that you can use with set pitch to set the pitch to those values. After those 2 lead-in notes, there are 3 copies of the pattern produced by the phrase function, right? So that's a total of like 36 notes here. This is the bulk of the song. But it's just 3 function calls now that we've defined that phrase function. The first and third copies start on B4, and the middle copy starts 1 step higher on C5. And again, you can just call set pitch and then call phrase to have that happen, assuming your phrase function works. After 3 copies of that common phrase, we go into the sort of like end game of the song. There's a middle-low pattern starting on C5, followed by a new 3-note sequence with pitches A4, D5, and C5. And for reference, A4 is 2 steps below D5, so it's A4, step up twice, D5, and then step down once, C5. So it's low, step up twice, step down once. And then finally, there's an up, down, down pattern starting on pitch B4. Again, use a combination of set pitch. For those 3 extra notes, you could use 3 notes, or you could use add note 3 times. Whatever you do, every time you add a note, no matter what the, all the notes except the first 2 and the last one are the same duration, but every time you add a note, that duration has to shorten by a factor of 0.99. The last note in the song is just a single ending note. It has double the standard note duration, so it's a sort of 2 note long note, and the pitch is G4. And so that double duration is based on the final shortened duration, right? So we shorten, and at the very end we have a double length note. The jig function needs to return not actually the duration of that note, but half its duration, right? The base duration of that note, not the actual duration of that note. So that if somebody wanted to come along and start adding more notes that fit into the rest of the jig, they would be at the same durations as the normal notes in the jig, not this double duration note. Your jig function should only call add note when it really needs to, which at minimum is like the first 2 notes and the final note. Everything else, it should rely on the pattern functions that you've already defined. And double check the rubric for the detailed core and extra requirements there. Just like pattern did, you're going to have to use variables to keep track of that decreasing note duration, right? You're calling pattern 3 times, but the second pattern needs to know what duration to start at based on the end of the first pattern. And that's why these pattern functions return those duration values, so you can use them. So we have provided a test jig function, and we've provided in the problem set description the correct output that you should see printed when that function is run. And then at the top of the problem set description page, we have that audio that we played at the beginning. That is produced by the test jig function. So you can just listen to that again if you want to hear what it should sound like. Some notes on sort of how to approach things and little caveats here. The names of your function must match the specific names of the rubric, and they have to have the right number of parameters as specified for each function. You're allowed to define and call extra functions if you wish, as long as these don't invalidate the rubric rules saying that like function A must call function B, right? So if the rubric says function A must call function B, and you're like, well, I want function A to call function C that calls function B, that wouldn't be allowed. But other than that, you're good to go. The longer a song is, the longer it will take Python to process it when it's asked to play or save the song. And so when you're testing, using sort of shorter values can help alleviate that problem, especially with the full jig. Expect to wait a few seconds, maybe even 10 to 20 seconds for the audio to play before the done playing track message is printed. I'll just remind people that without installing an extra module, you won't be able to play the songs directly from Python. You'll just get a saved WAV file that you can play in your whatever media player you normally use. If you go into Thonny, into the options menu, tools menu, manage packages, then you can search for a package called Simple Audio and install that package. And then you'll be able to listen to stuff directly from within Python. Like Python will be able to play the song for you. There's also, if you don't have it installed, whenever you run things, there will be a little message that prints out telling you, hey, you can do this to install. Another reminder, which I have sort of touched on throughout this, that we have this link for the diff checker tool, right? That can be helpful in checking these really long, really intricate series of text that should sort of match exactly. For grading purposes, your submitted code may not use the print function anywhere outside of the testing functions that we provided. Again, anything goes in the test function itself. And it doesn't matter if you comment that out or delete it or not before you submit, as long as that stuff is in the test function and not causing any syntax errors. But outside of that, don't use print. Now, you probably should use print if you want to debug and figure out what's going on. That's a great technique. But make sure you clean up those debugging print function calls when you are done. Because in certain cases, we'll test what gets printed. And if you're also printing some other stuff, we'll look at that stuff and go, this is wrong, even though the notes might be correct. As I just mentioned, use the test function to do any testing you'd like to do. We've included calls there that you can comment in and out to the test functions we mentioned already. And the final note is just that the durations that synth.py displays in all these example strings are rounded off to a certain number of decimal digits. Your code should not do any rounding of any values whatsoever. So that is it for me on this task. And there are other videos for the other tasks in this problem set.